In this video, I'm covering 9 exercises that are related to chapter 16. In each case, for each exercise, you can pause the video, do the exercise on your own, and then listen to my explanation. So, first question, which of the following nuclei is magnetically active and can be studied by NMR? Magnetically active nucleus is one that has overall nuclear magnetic spin. And for nucleus to have overall nuclear magnetic spin, it must have either odd number of protons or odd number of neutrons, or both, odd number of protons and odd number of neutrons. So those are magnetically active nuclei. Nuclei that have both even number of protons and even number of neutrons are not magnetically active. They don't have net overall magnetic spin. So carbon 12, 6 protons, 6 neutrons, that's not magnetically active. Oxygen 16, 8 protons, 8 neutrons, that's also not magnetically active. Helium 3, that's 2 protons and 1 neutron. So odd number of neutrons, that's magnetically active. We can actually study helium 3 by NMR. Since helium doesn't form compounds, there won't be much use to it, but still we could do it. We can observe it by NMR. Neon 20, 10 protons, 10 neutrons, that's not magnetically active. So correct answer is C, helium 3. Question number 2, mass spectroscopy can provide information about molar mass. Yes, that's M plus ion, so that peak will provide information about molar mass. Molecular formula, we can obtain molecular formula of a compound if we carry out high resolution mass spectrometry. So high resolution mass spectrometry can provide information about molecular formula. Identity of a compound, yes. Mass spectrum is fingerprint of a compound. So if we can match a compound with spectrum in a library, and there is good match, let's say 95% or better, then identity has been confirmed. And that means that answer is all of the above. So mass spectrometry can provide information about all 3 of these. Next question, the NMR spectrum of C3H6O2 is given below. What is a structural formula of a compound? We can see here 3 signals in proton NMR. This is obviously proton NMR. And we can see that signal at 8 is a singlet. At 8, typically it's an aldehyde proton that appears. And then we can see the other 2 signals. If you look at inflection of the integration curve, if you measure the height of signal at 8 and we take that as 1, you will see that signal at about 1.3, 1.35 corresponds to 3 hydrogens. Since we here have only 6 hydrogens, that can be only CH3 group, only 3 hydrogens on a carbon. And the next one must be CH2 because inflection of that curve is twice as high. So area under the peak is twice as much as peak at 8. And as I already mentioned, at 8, that's because of the chemical shift, that's typical chemical shift where aldehyde shows up, or aldehyde proton. Actually not typical, they more show up around 10, but in this case, as you will see, we have electronegative substituent attached to carbonyl carbon. So we have CH3 and CH2, and you can see because of the splitting that CH3 is split into 3, into triplet. That's next to 2. And CH2 methylene is split into quartet. So CH2 is next to 3, next to CH3. So CH2 and CH3 are next to each other. Typical ethyl group. Typical pattern we see in proton NMR for ethyl group. That means we have ethyl group and we have this, what we would consider to be at this point, aldehyde functionality. When you add all these atoms that show up in proton NMR, we can see C3H6O. And we have O2, so 1 oxygen is missing. So which of the 4 structures correspond to the structure that is represented by NMR? We have to add 1 more oxygen at the appropriate place, but we have ethyl group, this structural element that looks like an aldehyde, and additional oxygen. Obviously A doesn't fit because CH2 methylene and CH3 methyl have to be next to each other. B, that one actually fits because we have aldehyde group, we have ethyl group, and we have oxygen in the middle. And chemical shift of around 4.2 for methylene group indicates that it's methylene that is bonded to oxygen. Also, this, what we consider to be aldehyde proton, has been shifted from about 10 to 8. That's an indication that electronegative substituent is attached to carbonyl carbon. So B fits. C doesn't, because there should be two CH2 groups, and there are not, there's only one. And D also doesn't fit because we should see carboxylic acid proton, and that one typically shows up around 12. It may be shifted to 11, but typically 11, 12, 8, that cannot be carboxylic proton. So correct answer is B. Question number 4. Which of the following compounds has Mz of 102? So mass to charge ratio of 102. That really question means which of the following compounds has molecular mass of 102, because then it will exhibit Mz of 102. And simply you have to add atomic weights to end up with mass of 102. In this case, actually, to make things a little bit shorter and not add every single one, not calculate every single molecular mass, I'm going to do only correct answer, and that's C. So you have to figure out how many atoms are present in this molecule. So there are 5 carbons. It's a cyclopentane ring. Atomic mass is 12, so 5 times 12 is 60. So 5 carbons contribute 60 to molecular mass of this compound. There are 10 hydrogens, so make sure that you calculate hydrogens accurately. 10 hydrogens. Obviously, hydrogen has atomic mass of 1, so total 10. And 1 sulfur, atomic mass 32. So when we add all those up, that's 102. And so that's the compound with molecular mass of 102. Next question, which structural elements are present in the following molecule? So looking from the left, we can see around 3300 rather large hydroxyl group. So we can tell that this molecule has hydroxyl group, OH. And then the other characteristic structural element we can see between 2000 and 1600, we can see several small peaks. That's an indication of aromatic ring, of benzene ring. So we would draw a conclusion that this molecule has OH group and aromatic ring. And that's D. It cannot be carbonyl group. Carbonyl group with A has carbonyl group as possible choice. A and B actually have carbonyl group as possible choices. Carbonyl group will be strong, sharp peak between 1850 and 1650. And it will be typically strongest absorption in the spectrum. C has triple bond as a choice. That one would show up around 2200 as weak to moderately strong, sharp peak. We don't have anything there. So the only possible choice is D. Next, what is the structure of the compound with the molecular formula of C5H12O that is consistent with the following spectrum? So again, we look at IR spectrum and we can see hydroxyl group. When you look at 4 possible choices, hydroxyl group immediately eliminates A and B because A and B don't have hydroxyl group. They are not alcohols. Now IR doesn't provide any additional information, so we should move on to proton NMR. And what do we see in proton NMR? We can see confirmation for hydroxyl group around 3.6, 3.7, maybe 3.65. That one weak, small, broad peak, that's hydroxyl, that's hydrogen bonded proton. But then even more importantly, we can see these peaks due to hydrogens, due to protons. We can see at below 1, around 0.9, 3 hydrogens. And that's triplet. So 3 hydrogens, if that's split into triplet, it means 3 hydrogens are next to 2. On the neighboring carbon, there are 2 hydrogens. And then around 1.45, we can see signal due to 2 hydrogens. And that signal is split into quartet. So those 2 hydrogens are next to 3 hydrogens. So the neighboring carbon, there are 3 hydrogens. So 2 next to 3, 3 next to 2, again, typical pattern for the ethyl group. So this compound has ethyl group, and by now you already can guess the answer. Because C or D, only one would fit. But just to be certain, we have strong sharp peak that is singlet, and it's due to 6 hydrogens. That has to be 2 methyl groups, and those 2 methyl groups are next to atom or carbon that has no hydrogen substituents because they are not split. And the only structure that corresponds to it is structure D. Structure D has hydroxyl group, it has ethyl group, and that's bonded to carbon 2 of 2-methyl-2-butanol, and carbon 2 has no hydrogens, so ethyl group is not coupled to anything. And then you have 2 methyl groups, and they are not coupled to anything because they are attached to hydrogen that doesn't have, to carbon that doesn't have any hydrogens. So D is the only possible structure. Question 7 is an integrated spectroscopy problem. So you can pause video here, see these 2 spectra first, and those are IR and mass spectrum, and then on the next screen NMR spectra are shown. So you can pause video here, see these spectra, and then see next 2 spectra, so mass spectra and possible choices, and you can flip between the 2, rewind video back and forth, and try to answer question on your own. And then next I'm providing you the answer. So if you want to do question on your own, you can stop video here, and then next my answer follows. So we start by looking at IR spectrum. So what is the information that we can obtain from IR spectrum? We can see rather strong broad absorption around 3300. That's hydroxyl group. So we know that we have hydroxyl group as possible structural element. There are some peaks between 2000 and 1600, but it's difficult to make anything out of them. So there is really not much more useful information in IR spectrum. In mass spectrum, besides mass of 122, molecular mass of 122, we can see this cluster 77, 78, 79. That cluster is typical of benzene ring. So you would strongly suspect that besides hydroxyl group, our compound also has benzene ring. Now, since formula is C8H10O, then we already have molecular formula, and there is not much use for molecular mass. There is not much more information from this spectrum. You can look at fragmentation pattern, but it's maybe better use of your time to look now at mass spectra. Simply on the exam, your time is limited, and while you can go on and extract far more information from mass spectrum, often in case of integrated spectroscopy problems, where you're given a lot of information, and a lot of information is redundant, you can get same information from various spectra, you're better off looking at spectra with higher information content, and those are NMRs. So you look quickly at IR, NMR, see quickly what is there, what information you can quickly get from it, and then you look at NMR spectra, and only as needed you may want to go back to IR and mass spectrum, just in case you want to check something, or you may want to see to get some additional specific information. So now you can see in carbon 13 we have not only 6 different carbons, but also depth spectrum has provided us information about substitution of those carbons. So we can see that there is one methyl group, one methylene group, CH2, and then there are 4 carbons that have, well, 3 carbons appear to be actually aromatic carbons, 2 CH and 1 aromatic carbon, and then we have carbon around 155, such like that. That's actually most likely aromatic carbon. It's a little bit out of the range for aromatic carbons, 150, but that could be carbon that is attached to an electronegative substituent. So we can say probably 4 different aromatic carbons. Benzene ring has 6 carbons. Only 4 show up. That's an indication that symmetry is present in a molecule. And then we should, when we consider proton NMR, so aromatic carbon, and then in proton NMR, again, I won't go again over it, we can see ethyl group. We have seen it a number of times. From integration curve, you can see there is ethyl group. Now, around 5, we can see that small peak that corresponds, integration corresponds to 1 proton, and that small peak is broad peak. So that's most likely hydroxyl group, and that's hydroxyl group we have already seen in IR spectrum. You can also see that there are 4 aromatic protons. 4 protons on benzene ring. That means benzene ring is di-substituted. It has 2 substituents if it has only 4 protons left. And that means that we can eliminate structure C and structure B, or B and C, because B has 3 aromatic protons and C has 5 aromatic protons. Question is structure A or D correct? And only A has symmetry that is represented in carbon-13 NMR. That means 2 quaternary carbons, or 2 carbons without any substituents that are unique. One is bonded to hydroxyl group, the other one to ethyl group, and 2 CH carbons. Each CH signal represents 2 carbons because they are identical. So there are 2 pairs of identical CH carbons. And also in proton NMR, 2 pairs of identical protons. So structure A is correct. See, so this is what NMR spectra shows up, that we have this substitution pattern. So that corresponds to structure. Here are integration and structure A. Question 8. What is multiplicity of the underlying proton in a proton NMR spectrum? You may be able to tell that right from a line formula. If you're not, you may have to redraw this formula as a condensed or even complete structural formula. So on that underlying proton, you look on the neighboring carbon, how many hydrogens are there, and then you use formula of n plus 1, where n is number of neighboring hydrogens, to arrive at multiplicity. We can see only one neighboring methyl group, CH3, that has hydrogens on it. The other 2 carbons that are attached to carbon that is bonded to underlined hydrogen have no protons on them. So it's only 3 protons that will be splitting the underlined signal due to underlined hydrogen. So 3 plus 1 is 4, so signal is going to be quartet. And the final question, how many signals would you expect in carbon-13 NMR spectrum of the following compound? In this case, you go around the benzene ring. That's the only place where we can find carbon atoms. And you consider carbon attached to hydroxyl group. That's unique. There are no such carbons in the ring. Then we have carbon B. That one is next to hydroxyl group and in position 4 or directly across the ring from chlorine. Again, it's unique. There are no other carbons like that. Carbon C, equidistant 2 carbons from hydroxyl group and chlorine. Again, just 1 carbon like that. D is carbon that is next to carbon-chlorine group, or next to chlorine, and across the ring, position 4 from hydroxyl. Again, unique. Only 1 carbon of the ring is attached to chlorine. Again, unique carbon. And only 1 carbon is between hydroxyl and chlorines. So each of those 6 carbons is unique, and so you would expect 6 signals. So NMR spectrum here, carbon-13 NMR spectrum here would show 6 signals for 6 distinct carbons. So this completes our exercises of chapter 16.